Hello, welcome to another module in this massive open online course. So, we are looking at example problems in convex functions and convexity. Let us continue our discussion. So, we are looking at example problems in convex functions, and well, let us look at this problem number 5. F of x bar equals x1 x2 for the region where both x1 x2 are greater than or equal to 0. We want to ask, the question is f of x bar. Of course, x bar, you can think of this as the 2-dimensional vector. This is a function of 2 variables, x1 x2. We want to ask, is this convex or concave? Convex, concave, or neither. Remember, it function need not be only either convex or concave, but can be neither convex or concave. All right. So, that is an important point to keep in mind. Okay. Let us start by looking at, once again, remember we have a simple test for convexity, that is the Hessian, which in this case is simply dou square f by dou x1 square dou square f by dou x2 square. These are the two diagonal elements, and the off diagonal elements are dou square f by dou x1 partial with respect to x1 x2 partial with respect to x1 and x2, and this is equal to, if you look at this, partial with respect to the first partial with respect to x1 is x2, partial with respect to x1 of x2. So, you can evaluate this as follows: dou partial second order partial with respect to x1 is partial with respect to x1 of partial with respect to x1, but partial with respect to x1 is x2. So, this is partial with respect to x1 of x2, which is 0. So, you can see this is 0. Partial with respect to x1 x2, you can see this is 1. Partial with respect to x1 x2 is 1. Second order partial with respect to x2 is also 0. Now, first thing you can see is this is a symmetric matrix, correct. So, this matrix here, the Hessian, is a symmetric matrix, but this is not positive semi-definite. This is not a positive semi-definite. In fact, if you look at the determinant of this, this is 0 minus 1 equals minus 1, this is negative. Okay. So, the determinant is negative. Remember, the determinant of a positive semi-definite matrix has to be a positive quantity, because the determinant is a product of the eigenvalues. All of these eigenvalues are either are non-negative, therefore, the determinant has to be greater than or equal to 0 for a positive semi-definite matrix. All right. In fact, if you compute the eigenvalues, that is, find the characteristic polynomial minus lambda times I and take the determinant, this is equal to determinant of 0 1 1 0 minus lambda times 1 0 0 1, and you take the determinant of this, that is equal to minus lambda minus lambda 1 1 minus lambda, and if you take the determinant of this, that is basically lambda square minus 1, and lambda square minus 1 equals 0 implies basically lambda equals plus or minus 1, and you can see the eigenvalues are both positive and negative. It has a positive eigenvalue and a negative eigenvalue. And negative. So, implies matrix, remember positive semi-definite matrix has only non-negative, that is eigenvalues are greater than or equal to 0. Here you have a negative eigenvalue, that is minus 1, which implies the Hessian is not positive semi-definite, and therefore f of x bar is not convex. Implies delta square f of x bar is not positive semi-definite, implies f of x bar is not convex. Now, what about concavity? For that, consider minus x f tilde equals minus f x bar equals, remember f of x is concave if minus f of x is convex. So, we consider minus x1 x2. Now, consider the Hessian of f tilde. The Hessian of f tilde is simply the Hessian minus of the Hessian of x bar. So, this will be 0 minus 1 minus 1 0. Now, again check the eigenvalues, delta square f tilde, the Hessian minus lambda I, determinant. Look at the determinant of the Hessian. This will be the determinant of, well, minus lambda minus 1 minus 1 minus lambda equals once again lambda square minus 1, and once again lambda square minus 1 equals 0, implies lambda equals plus or minus 1. Again, the Hessian of f tilde is not positive semi-definite, which means Hessian of f, which means f tilde is not convex, and therefore f is not concave. Remember, f is concave only if f tilde, that is minus of f, is convex. So, this implies f tilde x bar equals minus of f of x bar is not convex, implies f of x bar is not concave. F of x bar is not concave. Now, so f of x, so x1 x2, you can see it is very interesting, it is neither convex nor concave, alright. That shows that any function does not always mean, if it is not convex, does not automatically mean that it is concave, alright. There can be functions which are neither convex and concave, and that is easy to see, because if you have a function that looks something like this, it is neither convex nor concave, okay. And so these kind of functions, these are neither convex nor concave. Okay, something to keep in mind. Okay. How about quasi convexity? Now, for quasi convexity, remember you have to look at the level sets S of t equals x bar such that x1 x2 less than equal to t. Now, if you look at the set x1 x2 less than equal to t, what you will observe is that if you plot this, if you look at the set x1 x2 less than equal to t, that will be this set. This is the curve x1 x2 equals t. and this is the area that is x1 x2 less than equal to t, and you can see this set is not convex. This set is not convex. On the other hand, if you look at the super level set, that is x1 x2 greater than or equal to t, this is a convex set, because if you take any 2 points, join them by a line, it lies in this. So, this set, the super level set x1 x2 greater than or equal to, this is a convex set. Okay, so implies thus not the sub level set, super level sets equals are convex, that is super level set. Sub level set, remember, is the set such that x1 x2 is less than equal to t. Super level set is the set x1 x2 greater than or equal to t for any parameter value of the parameter t. So, the super level sets are convex, which means this is a quasi concave function, implies this is a quasi concave. This is a quasi concave. So, x1 x2 is neither convex nor concave, it is a quasi concave function. Okay. Similarly, let us now move on to the next example. Let us now consider the reciprocal of the previous one, f of x bar equals 1 over x1 x2. Again we want to ask the same question, is this function 1 over x1 x2, is it convex or is it concave? And you can once again find the Hessian of this. The Hessian of this will be, well, let us first start with the gradient. X bar is again the 2-dimensional vector. This is a function of 2 variables x1 x2. So, the gradient with respect to x1 x2 will be well, this will be derivative with respect to x1, that will be minus 1 over x1 square x2, derivative with respect to x2 will be minus 1 over x1 x2 square, and now the Hessian will be, take the first element, differentiate it with respect to x1. So, that will be 2 over x1 cube x2, and now differentiate the first element with respect to x2. So, this will be 1 over x1 square x2 square, this will be 1 over symmetric. So, this element will also be 1 over x1 square by x2 square. The 2 cross 2 element will be, well, that will be 2 over x1 x2 cube. Okay, and now we have to see what is the, is this matrix positive semi definite, and you can simplify this by bringing x1 cube x2 cube outside. This will be 1 over x1 cube x2 cube times well, times this is twice x2 square twice x1 square, and this will be x1 x2 x1 x2. Now, we want to ask the question, is this matrix positive semi definite? This is the Hessian, and we want to ask the question, is this matrix positive semi definite? Now, there are many ways to show this. If the matrix is positive semi definite, one of the methods is of course to compute the eigenvalues, which might be slightly tedious. What we are going to do here is we are going to decompose this in the form of factors which are A times A transpose, alright. Now remember, each such factor is positive semi-definite. We said that if a matrix can be expressed as A transpose, this is positive semi-definite, and the sum of such positive semi-definite matrices is positive definite. So, we are going to factorize this into a sum of matrices which can be expressed in this form. Okay. And you can clearly see it is not very difficult. You can first write this as x1 cube, x2 cube, you can write this as x1 or x2 square, x1 x2, x1 x2, x1 square, x1 square plus this will be 1 over x1 cube, x2 cube, x2 square 0 0 x1, and this will be, now I can decompose this into factors. Now you can see this will be 1 over x1 cube, x2 cube times x2 or x2 x1 times x2 x1, that is, this is of the form vector A bar into A bar transpose, plus obviously the next one you can easily see that this is x1 cube, x2 cube, diagonal matrix x2 0 x1 0 times x2 0, and this will be a matrix of the form BB transpose. Okay, so, we are decomposed it into the sum of matrices which are factorized as AA transpose. So, each of these matrices, component matrices, is positive semi-definite, therefore, the sum is positive semi-definite. You can easily see that if two matrices are positive semi-definite, alright, compatible matrices, if you sum them you get another positive semi-definite matrix. Okay, so, this is positive semi-definite, this is positive semi-definite, and therefore, this implies that basically your matrix, this implies that this is the sum of two positive semi-definite matrices. Remember that this is also only for x1 comma x2 greater than or equal to 0, which means these factors, that is, if you look at these factors 1 over x1 cube, x2 cube is are also greater than or equal to 0. Therefore, this is positive semi-definite matrices weighted by positive factors. So, these are positive, these are positive, so the resulting matrix is positive semi-definite. So, that means the Hessian is positive semi-definite. Okay, Hessian is positive semi-definite. Remember this notation, which implies that f of x bar equals convex, and it can also be seen that since it is convex, it is also quasi convex, because any convex function is also quasi convex. Okay, so, this implies that f of x bar also quasi convex. So, it is 1 over x1 x2. Remember, what is f of x bar? F of x bar, this is 1 over x1 x2, this is quasi convex. Right. So, 1 over x1 x2 is basically convex, and hence it is also quasi convex. Let us look at another example. and this is, you can treat this as a practical application. In fact, it is a very interesting we are going to look at the entropy function. That is, which can be defined as the entropy of a source, H can be defined as minus summation, or entropy of a minus summation I equals 1 to n xi log to the base e natural log xi, okay, where xi equals probability of the ith symbol. This is the probability of the ith symbol, and this entropy denotes the information content of the source. This entropy, it denotes the information content of the source, that is, given a source with n symbols which have probabilities x1, x2 up to xn, what is the average information content per symbol of this source, that is given by the entropy, that is minus summation xi log log of xi. And therefore, the higher the entropy, it means the higher the information content of the source, and therefore, we would like to maximize this entropy quantity, and that has very important applications in information theory. So, we would like to maximize the entropy or the information content. Okay. So, this has applications in information theory. Okay. So, this is a very important quantity in information theory, and by extension in also wireless communication and signal processing. In fact, many fields, machine learning also, since information theory has widespread applications in several, right, as several applications as several applications in various fields, all right. So, therefore, this quantity entropy is very important. Now, what we want to show is that this quantity entropy is a concave quantity, and that is relatively easy to show. We start by considering f of x equals x log x, that is the natural logarithm, and we demonstrate that this is convex. You take the first derivative, this is very simple, this is x, so we use the product rule. So, first differentiate with respect to x, that is 1 times log x plus x into the derivative of log x, which is 1 over x, which is basically log x plus 1. And now, if you look at the second derivative, that will be derivative of log x, which is 1 over x plus 0, which is 1 over x, that is greater than or equal to 0. So, this implies x log x Hessian is greater than or equal to 0, this implies x log x, or second derivative is greater than or equal to 0, implies x log x is convex, which implies that minus x log x equals concave. Okay. And therefore, now if you look at the entropy, log to the base. You can see this is the sum of concave functions. Implies this is concave. So, the entropy is the sum of concave functions, and therefore, this is in turn concave, and therefore, one can maximize the entropy, thus maximizing the average information of the given source. All right. So, we will stop here and continue in the subsequent modules. Thank you very much.